Right, so next up is Raph Levien. He is on the Google Fonts team and specifically working on GPU font rendering. He's launched the pull-down CMark project, which has now been given to the community, and a large community is actually building on that. You've been working on many things, Velo, Xylem. Last year you talked about Xylem at Rustenel, and now you're going to talk about Velo. You've just been recompiling your slides to make page down work, I think.
Yeah, we have page down, so, named key, page down.
And I also think that you have a very interesting t-shirt. What does it say?
Yes, with undefined behavior, anything is possible.
We live for that. All right, take it away, Raph.
Thank you, Terts. All right, so today I'm going to talk about the evolution of Velo to be faster and I think most importantly, easier. I'm glad Terts mentioned pull-down CMark because this is I do a lot of researchy things, and pull-down CMark is like one of the few Rust things that I've done that's actually like really in production, and I kind of want to recapitulate that. That I want to make 2D rendering easy and something that people can just reach for and have. So I want to talk a little bit about the current state of the Velo GPU renderer. I think it has a lot of it's research that really advances the state of the art of rendering, but there are definitely challenges. Like if you want to put it into production, then you're going to run into at least one of these challenges. So one of them is that it is based on compute shaders, and compute shaders are a relatively recent feature. It's hard to know for sure whether your GPU is going to support that. And certainly if you want to deploy your app on WebGL, you do not have compute shaders. Another challenge that people have run into is the memory usage, that the default configuration is quite a bit of memory, and a bigger problem is that it's unpredictable. So if you specify such and such buffer size, and then you have a bigger CAD drawing that you need to bring in that overflows that buffer, then it will fail. And this is one of the things that's really challenging about kind of compute GPU programming. The architecture is based on compute shaders, and most existing renderers, like if you look at Bevy or some other game engine, it's going to not be based on compute shaders, but based on the rasterization pipeline. And so if you want to take the output from Velo and blend that into your renderer, it's not that easy to do. There's some performance cliffs, like if you zoom way in or zoom way out, then the performance falls down. And just generally, like it's a difficult code base to get into. So those are the challenges that we want to address with this new work, this evolution. The key advance, the kind of technological advance, is this idea called sparse strips. And sparse strips is both a representation of the rendered path that you get, and it's also the algorithm for rendering that path. And so the idea, a sparse strip is geometry that has fixed height. We're experimenting with both 4 or 8 pixels for the height, and then the width is variable. And so it's an efficient representation of the rendered path. The idea is that it takes fairly minimal memory usage and also a fairly small number of primitives to render, because when you bring this to the GPU, then there's a cost per primitive, and it's efficient to calculate. So there's a wall of text here. I'm not going to walk through that. I will show you with an animation that I've been working on. So let's say we want to render this shape. We want to render this R, and it has a mixture of line segments and curve segments, Bezier curves. So the first step in the pipeline is that we will take the curve segments and flatten them to lines with some tolerance, adjustable tolerance, obviously. So you tune it so that it's you don't see it visually. So now we have the shape entirely made out of line segments. The next step in the pipeline is that we are going to divide it into tiles. And here a tile is going to be, we're going to use 4x4 for the tiles here. And so we put a grid over the line segments. And then the next step is to generate tiles from that, for each line segment in the shape. We're going to identify which tiles are covered by that line, and for each tile that it covers, we're gonna generate an element in this tile array that has the x and y coordinate of which tile it came from, and also the clipped geometry of that line. So now that we have all of the tiles to render this shape, the next thing that we're going to do is sort. And this is actually just regular call to sort unstable is good enough for the ordering guarantees. And so now these are sorted by in scanline order. So there's an XY coordinate, and those just increase for the tiles in the shape. And that sorting, that's really one of the critical things. That solves a lot of problems for us. And in particular, all of the tile segments that are in the same geometry, in the same tile location in the original, are now a contiguous slice. So we're going to take those contiguous slices, identify them, and merge them. So for each merged tile, we now have a slice of the tiles. Now that we have the merged tiles, that contains all of the information that we need to render the pixels. So we're going to take that merged tile and just compute a 4x4 grid of alpha values. And that's a fairly simple calculation. We're just computing the percent area of each pixel within that tile that is covered by the line segments in that merged tile. It's about 90 lines of code. It's not an incredibly complicated calculation. So now we have the rendered pixels for each of the merged tiles, and the next step in the process is to organize those into strips. So this is the sparse strip idea. Now we're seeing the strips from the sparse strip idea. And so each one of these strips is going to become a quad that is sent to the GPU. And again, the reason for combining these into strips is to reduce the number of quads that need to be rendered. We could send each tile individually, but that would be a lot more tiles. And we want to make the GPU computation as efficient as possible. So we organize into strips, and then we send them to the GPU to get rendered in the XY location. And there we have it. There's also, I didn't animate this, there's also this question of filling in the sparse fills, the areas that don't have alpha values, but that's just filling a solid rectangle, which is like the simplest and most efficient thing that you could possibly do on a GPU. So that's the central engine behind this algorithm. And I was doing experiments late last year of doing a CPU implementation of this kind of as an intermediate step towards, okay, we want to get this running on the GPU, get it faster. But what I found is that running this on the CPU is really fast. Like it is, I think the experiments that I was doing showed it about 2.5 times faster than TinySkia, which is very efficient. TinySkia is very good code. We drew a lot of inspiration from it. And it's also faster than Skia software. It's faster than renderers that are in production. So there's a spectrum. There's like many different modes that will be shipping this sparse strip idea. And one of them is a purely CPU implementation. And so that's very portable. It'll run essentially everywhere. It's no-stid. And it's a small, simple code base. So if you are on a server and you don't want to deal with getting your GPU configured, then you can just call into Vevel CPU and have a pretty good performance renderer without any of the difficulty of the GPU infrastructure. And one of the reasons why we're getting good performance, I'll talk a little bit more about this later, is SIMD optimization, the ability to use that parallelism at the CPU level. Now, of course, CPU-only rendering, there's a speed limit. Like you do not want to do the pixels on the CPU if you have a possibility of computing the pixels on the GPU. It's order of magnitude more throughput. So the mode that I'm really focusing on today is the Velo hybrid mode, which basically says that you do your geometry and your scheduling, you do that sort on the CPU on tiles, so you're not doing the per pixel work on the CPU, you do all of the per pixel work on the GPU. So you do this tiling, you upload that work, it gets evaluated on the GPU. Right now, we're doing the alpha values also on CPU, but the next step soon is to move that work to a compute shader as well. And then the fully GPU-driven mode. We want to get there, but that's an open research topic. There are many, many difficult problems that you have to solve to really get this, memory efficient and so on and so forth. And so this is going to be work going forward. So for today, we're focusing on the Vell hybrid mode, where you have this mix of CPU and GPU. So the performance philosophy is that as opposed to the Velo that you might have seen a year or two ago, that we are moving some of the allocation and scheduling work to the CPU just because of how difficult it is to get that fully GPU driven, and then do all of the per pixel calculation on the GPU, really focus on SIMD and eventually multi-threading for the CPU work so we can take advantage of as much parallelism as possible on the CPU. A really important direction for performance is caching. So this depends on your application. If you have a fully dynamic scene, then caching is not very important. But if you want to render a UI, then all of those glyphs are cacheable, and so you don't want to keep re-rendering them. And then, given that we have the CPU to do the scheduling and allocation work, once we decide what work needs to be done, we want to move that to the GPU so that that work is as efficient as possible. So it's sparse. We want to avoid any unneeded work. Like if there's a region that doesn't have any coverage, then you don't want to do any work at all. And then this is a more technical thing that we want to minimize the barriers, because a lot of times if you have a lot of draw calls and you have pipeline dependencies, then that can be a slowdown. And so this is a real goal, is to pack as much as possible into a draw call so that the number of barriers is minimized. And a really important part in terms of putting this into production is that we are using bounded memory on the GPU, no matter how complex the scene gets. If you overflow a buffer, then you issue the draw call, and you do as much as possible within a draw call, issue that draw call, and then go to the next draw call to do the rest of the scene. So you don't have unbounded memory usage. So as I say, path caching is a really important part. This is not actually implemented yet. This is part of the plan, but to avoid the dynamic rendering of all paths, when you have that path already rendered, you use that sparse strip representation, which is very memory efficient, especially as you're, like if you have glyphs, like the classic glyph atlas really only works for small glyphs, because if you have a large glyph, you have so much area, it's n squared, but the sparse strip representation is linear. We also can avoid a little bit of complexity because the layout of the alpha values is linear, so you don't have to do this 2D allocation in a glyph atlas. Yeah, so this really is showing you that efficient scaling, that if you have a small glyph, then it's really dense. You don't get any value out of the sparseness. But on the other hand, it's very efficient on the GPU because rendering these strips is essentially as fast as if you were rendering a single quad out of a glyph atlas. You've got a little bit more vertex work, but on the other hand, you're saving in fragment work because any coverage that is not, that's not actually covered by the glyph, then you don't even schedule those fragment shaders. Then as your glyph gets larger, then you really get a tremendous amount of advantage from the sparseness, because you're really only storing the alpha values on the edge of the glyph, and those large regions that are empty, or those large regions that are completely filled, don't take any memory. So another optimization that this is actually landed it's fully landed in the CPU, and there's a PR in flight for it to land in hybrid, is clip optimization. So let's say that we have some simple shape that we're using to clip some contents, in this case text. And so this is one of the things you have to do in a 2D renderer. It's not like, this is different than 3D rendering, where you pretty much just painter's algorithm and draw the things. Sometimes you have these trees, you can have nested clips, and so it can get quite complicated. And this is challenging. Like Tiny Skia will composite all of the, it'll draw the inner contents, and it'll draw the mask, and then it'll composite everything. And that is a real performance problem. So we want to optimize this again, the philosophy of making the GPU work as efficient as possible. So we classify every tile in the clip path into basically 3 possibilities. So if you're in the interior of the clip, then you just draw. You just do the same drawing of the interior contents without doing any special processing for the clip at all. If you have nothing to draw, or if you have no clip path, then you don't schedule any work to the GPU. You don't need to draw any pixels, so don't draw anything. And then for the third classification, for the things that actually have some alpha values in the mask, then you do compositing. You render the mask, you render the interior content, and you do a compositing operation on those tiles, right? So I think that clip optimization, I think this is one of the reasons why we will expect really world-class performance from this renderer. And so there's those tiles to composite. There's an intermediate buffer that needs to store those rendered, the rendered content that you'll be clipping. And this is a challenging thing. So the idea here is what I call spatiotemporal allocation. So this is rendered kind of abstractly, where each of those nodes in the tree is representing some kind of compositing operation, maybe a clip compositing where you take the mask and composite it with the content, or maybe a blend, maybe something like hard light. Like all of that uses the same infrastructure where you need to have some intermediate texture representation and then do some work based on that. So if you have abundant memory, then you do all of the individual elements that needed to be composited in parallel. But of course, you've got data dependencies, so you need to schedule multiple draw calls to get those dependencies resolved. If you have tight memory, on the other hand, if you're working in a bounded buffer space, then maybe you don't have space for all of those tiles, and so you are going to spatiotemporally allocate those. You're going to move those out in time so that each individual draw call is going to be only needing a bounded number of tiles. Great. All right, so again, parallelism is the name of the game. This comes from GPU land, where you have massive parallelism, where if you are not able to express your problem in at least 10,000 threads, you're not using the hardware. On a CPU, you don't have tens of thousands of threads, but you may have a dozen. So all of the early pipeline stages up to coarse rasterization are fully parallel by draw object. So you render all of the paths. They're all completely independent of each other. There's no need to serialize that. So you can effectively just put those out to Rayon and have them all rendered in parallel. Then there's this coarse rasterization step. Currently, this is taking, for some of our tests, it's taking 2% of the total time. So this is potentially your serial bottleneck, but it's fast. And it's a relatively simple calculation per tile, per one of those wide tiles. That's not a 4x4 tile, that's about 1,000 pixels. And then lastly, on the CPU, you have this fine rasterization step, and again, that's fully parallel. That once you've done the coarse rasterization, there's no dependencies from one tile to another, so you can just farm those out to all the cores on your computer. And of course, if it's a GPU, then you're using those tens of thousands of threads that are available. And one of the things that we've been exploring more and more is that for the stages of the computation that are on the CPU, you really want to use SIMD. So again, coming from GPU land, there's this massive amount of parallelism that's available. Why not exploit that parallelism by using the SIMD lanes on your chip? SIMD is single instruction multiple data, and it basically it's on all modern computers these days. And the idea is that instead of just saying, multiply 2 numbers together, you can say, here's a vector of 16 numbers, multiply all of them together, and that happens in 1 clock cycle just as fast as the scalar. So it's a really significant increase in throughput compared with being able to do just scalar computations. And we've been finding, again, coming from GPU land, that we can use the SIMD for all of the stages of the pipeline that are performance critical. The flattening, the tiling, the rendering of those alpha values, as long as those are going to be on the CPU, and then the fine rasterization, the per pixel. Also, you can really exploit that SIMD parallelism. One of the things that I have been particularly excited about is Neon FP16. So this is, one of the nice things about AI is that people start to care a little bit more about these smaller data types. And FP16, you can get twice the bandwidth, twice the throughput, as if you're using 32-bit floats. And so that's particularly important on things like Apple Silicon and also Android phones. Those generally have this 16-bit capability. One of the challenges is that my experiments, I am writing that in assembly code because Rust doesn't really have support for FP16 SIMD yet. So one of the things that I am hoping to do this week is to talk to people on the compiler team, Rust project, who are working on SIMD, because I have a lot of ideas about how we should do this. So if you're working on SIMD, let's talk. Okay, so this project, the community aspect of this project is, to me, it's really been incredibly gratifying. The team has come together. We have 3 people. Taj and Alex are here from Canva today. Actually, well, let's see. Taj, Alex, Laura, Tom, Daniel, and Nico are here. So you'll be able to meet most of the team. And in addition, Lorenz Stampfel from ETH Zurich, he is doing his master's degree on the CPU version and basically exploring how far can we get on the speed up of the CPU version. And then also Tom Churchman has been working independently. Daniel is funded by Google Fonts, part of Linebinder organization. And Nico Burns, who's also here, is on the Blitz project, which is part of Dioxys and driving a lot of the Blitz use cases. We have renderer office hours every Wednesday. There's also transcripts of those available if you want to read that. And I really want to recommend, come to the Linebinder community for learning and building some of this infrastructure. I think I'll show a demo of Blitz here. This is using, all these demos came together just in the last week, in fact. And so Blitz is essentially a small fragment of a web browser that's really designed to render applications, but it can render web pages. So here we are rendering rust.org, rustlang.org. And it's not complete. It doesn't have complete rendering fidelity, but it gets a lot of stuff on the screen. And this is using CPU, by the way. This is perfectly good, perfectly usable, dynamically rendering all of the glyphs. Like by the time we're done with the performance optimizations, even on CPU, it's going to be quite usable. And of course, when we move the pixel rendering to the GPU, it'll be really fast. Another demo that I found is Josh Camo's page on CSS shadows. We do implement these blurred rounded rectangles. That's one of the rendering primitives. And so that's part of the imaging model. Let's see. So I have a little demo on the, let's see, this is RunWasm WebGL. All right, here we go. Okay, this is Velo Hybrid. This is a relatively simple demo. It's just a SVG renderer rendering the standard tiger image, which is sort of hello world of vector. So this is running in the hybrid mode. So the pixel rendering is all being done on the GPU. And then I have, let's see if this works. I have a demo of this running in WebGL. So this is running without compute shaders. In WASM. And let's see here. That's my Chrome window. Do I have to exit? Make this work. There we go. And so there's your GhostScript Tiger running with WebGL. So we run on down level GPUs. All right. Great. So current status. So we just did a release late last week of Velo CPU 0.0.1. It's still, I would consider, alpha quality, but you can absolutely get started on this. It has Lawrence has been doing incredible work on this. And so the imaging model includes now gradients. The gradients, you can specify the color space using the color crate. It supports images, different interpolation modes, clips, blends, blurred rounded rectangles. The text supports variable fonts, hinting, and also both color v1 and bitmap emoji. And so I actually think that Rendering emoji, this is one of the use cases of why you would want to do Velo CPU. If you're rendering these small things, spinning up a GPU infrastructure doesn't make a lot of sense. But if you say, I just want this emoji rendered, then it's a great solution to that problem. Velo CPU is also no-std. When I showed you that Blitz demo, that was going through an any render abstraction so that you can choose like which renderer you want to do. And Velo CPU is one of the supported backends of that abstraction. Velo Hybrid is not quite as far along, but it's in very active development. We're making, the rate of progress is amazing. If we count PRs that are in flight, then we have images and clips, and we have that WebGL2 backend that does not depend on WGPU. So it is a very lightweight dependency. Roadmap, we have, of course, a lot of ambitious stuff we want to do. There's a full roadmap doc that you can go to. We want to really complete the imaging model. It's really almost done for CPU, but really complete it on hybrid. Build a set of image filters for both the CPU and the GPU modes, things like blur and stuff like that. Obviously, we want to do a lot of performance work, including the glyph caching, and then some really advanced things like HDR color and conflation-free compositing for the future. All right, that's my talk. I'll take questions.
Thank you. Thank you so much. Great talk. Are there any questions? In the meantime, I'll apologize for the flickering that was on screen. We'll try to get it fixed. There was a little bit of...
I didn't see it.
We're looking into it. Don't worry. We'll get it fixed. Where is the catch box gone?
Hi. Great talk. Thanks. My question is, why 4x4 tiles, and what are the trade-offs involved in choosing that size?
There's a bunch of Zulip threads on this exact question. So the trade-off, the essential trade-off is the amount of work that you have to do to create those tiles and sort those. So a larger tile will reduce the amount of sorting work. But the other side of that trade-off is that if you have a larger tile, then some of those pixels in those tiles are going to be either all 0 or all 1. So you're doing more work per pixel. There's a much more complicated trade-off. I think we will probably go to an 8x8 tile for most of this, just to reduce, if you've got the GPU doing the alpha rendering, then you probably want the 8x8 tile because the cost of those wasted pixels is much lower, and then you're really focused on the CPU side of getting those tiles sorted, so getting fewer tiles is better. But yeah, ultimately it's an engineering trade-off that you look at the relative costs and then pick the tile size that gives you the highest performance.
All right, next question.
Thanks, I appreciated the talk. You focused a lot on the rendering backend, and the performance seems very impressive, but I was curious what work there is to integrate this with existing Rust UI libraries, and how similar the API actually is to some other library like TinySkia or the things you were listing.
Yeah. So these are both ongoing, ongoing projects. So we are building this for Xylem. I was not able today to show a demo of Xylem rendering with this renderer, but that's obviously coming soon. In terms of the API, we're actually not completely settled on the API. That one of the things that we're wrestling with is, do we do an abstraction? And Nico's work on any renderer is kind of a snapshot of what that abstraction might look like. Or do we want to expose kind of lower level primitives? And I think ultimately that's going to depend on the application. The API is pretty easy. It's not that different than TinySkia. There are important differences. Like TinySkia, those are immediate mode rendering primitives on a PIX map, and that won't fly if you're on a GPU. And that's actually, for example, the thing about compositing and with the clip optimization, that you really need to have more intelligence where you have both the contents and the clip path before you can decide what work is needed. So there's a little bit more batching and stuff like that in the API. It's not exactly the same, but it's pretty easy to use. It's not really painful. Hope that answers the question.
All right.
Yeah. You mentioned that there's currently hybrid is the most developed, but you're working on doing a full GPU implementation.
Yeah.
Is the limitation like GPU APIs or hardware features, or is there some aspect to those problems that is like inherently non-GPU friendly? Curious.
Yeah, no, it's a great question, and I have this other blog post called I think I Won a Good Parallel Computer that goes into those. It goes a little deeper into that exact set of questions. So it's not a limitation of parallelism. I can exploit as much parallelism as available, but there are important limitations in the GPU execution model, right? Where the GPU, the way GPUs generally work today, that you want to submit all of the work up front, and then when you have intermediate buffers, you can't dynamically resize them in the middle of the computation. Though that's just not part of the standard GPU model. So it's really those limitations. But in terms of being able to exploit, tens of thousands, hundreds of thousands of threads, that's not the limitation at all. So I'm hoping to, explore like advanced GPU features like work graphs and stuff like that, which are more dynamic in their ability to schedule work. That's kind of why it's research.
Okay, cool. Thank you.
All right, there's another question over here. You've got the box.
Oh.
You did have a question?
Yeah. Where can I buy one of those shirts?
There is if you go to the blog post, I think the blog post is called exactly this, with undefined behavior. There is a T-shirt purchase link, and I think the proceeds go to Amnesty International.
All right, question
Hello.
answered, I think. There's another one over here.
Yeah. So thank you so much for your talk. So my question is, I saw in the GitHub repo that there is like it has a predecessor, right, called Piet, if I'm not mistaken.
Yes.
What would be the main changes between Piet and Vell? Thank you.
Absolutely. So Piet really was designed as an abstraction over the platform rendering capability. So Piet would delegate to direct 2D or core graphics or something like that. So here the focus is really implementing the renderer logic ourselves. Another very important difference is, this is a huge evolution, is that Piet was also delegating to the platform to do text layout. But now we're building, also part of the larger Linebender project, that we're building a really robust production quality text stack. A lot of that infrastructure is being shared with Chrome. So you may have seen some blog post about memory safe font loading in Chrome. That is all the same infrastructure. A lot of that is developed by the Google Fonts team, and obviously we're using that in Linebender. We're dividing the responsibility that text layout is not the responsibility of Vell. You call into Parley to do, or Cosmic Text, we actually give you both choices, to do the text layout, and then Vell renders the glyphs, the emojis, the variable fonts. And so that's a very important distinction, because in Piet it was like, the text layout was actually part of the scope.
There's another question here. Yeah.
Yeah.
Go ahead.
Me first? Okay, hi. Yeah, thank you so much for a great talk. It's amazing. Like you, I am very excited about dynamic work graphs and the shiny feature of dynamic allocations on the GPU and all that happening.
Mm-hmm.
At the same time, it feels far away on something like web GPU.
Yes.
So is your opinion work graphs are bust, or is there something that one might imagine that ever happens with web GPU here?
Okay, so that's a deep question. I think work graphs right now are not fully baked. I think a little bit more evolution needs to happen. So how long is that going to take, and how long is that going to take before it's like standardized and available in web GPU? I can't even start to say. So that really is why we're focusing on these hybrid modes, so that we can get you a renderer. We want to get you a production quality renderer in your hands that you can integrate in your application and use today, and not wait on this kind of advanced research.
Okay, and then let's do the last question here in the front. Sure.
Yeah, so you mentioned sort of comparing to the the text rendering, or sorry, the system rendering for
Mm-hmm.
text.
Mm-hmm.
I've noticed that there's pretty widely varying results from different font renderers, depending on what application I'm using. And I'm wondering, is there like a standard way to actually evaluate your rendering and how it looks on a given screen, or is that just kind of...
It's a good question. I don't think there's a standard way of rendering. Obviously, being on the Google Fonts team, text is one of our top priorities, and our goal is to get text rendering quality that is top notch, and which is hard, by the way. So, the Scrifa level, the font loading level, now does have hinting and auto hinting. That is actually the auto hinting is exact match for free type, which is very high quality. That's all work by Chad Brokaw. The other challenge that we don't do yet is the subpixel RGB rendering. This is also planned, but I'm not going to promise when that's available. So, our goal is to have the absolute top tier of text rendering quality, and we will get there.
Nice. That's a very good last question and a very nice answer. Thank you very much, Raph Levien.